Welcome to the virtual classroom. Today we're going to be talking about Lagrange interpolating polynomials and their associated theoretical bound. And I copy-pasted this from our last notebook. These polynomials here, they're a degree 1 polynomial. They're a function that depends on x, dependence on x here, and this is x to the power 1 basically. And this are constants, right? Because this is for a polynomial going through 2 points. Those 2 points are x naught and its corresponding value f of x naught and x1 f of x1. Okay, we previously might have, instead of writing f of x naught here, we could have written down y naught, the corresponding output value. Similarly here, instead of f of x1, we could have written down y1, the corresponding output value there. Now these, they don't have a formal name. They're kind of a helper in defining the polynomials, the Lagrange polynomials. So these intermediate, or sometimes switch polynomials, appear in the definition of the Lagrange interpolating polynomials that interpolate 2 data points. Those are my 2 data points, x naught, y naught, x1, y1, and we can write down the Lagrange interpolating polynomial, and I won't use any subscripts here, and I use the switch polynomials L naught of x with f of x naught plus L1 of x f of x1. Now here f is an unknown function that generates the data, but discovering it, the function f precisely, might not be possible. So instead, we approximate f with the Lagrange interpolating polynomial. In the case of 2 data points, this is the best we can do. Now remember, f of x naught is y naught, and f of x1 is y1, and so we get x minus x1 divided by x naught minus x1 multiplied by y naught, the whole thing multiplied by y naught, plus x minus x naught divided by x1 minus x naught, the whole thing multiplied by y1. And you might already be thinking, how do you remember which subscripts go where? And I'll start telling you that. First of all, here's the independent variable, right? The x here and here. Now when we switch x with, let's say, x1, when I put x1 here, x1 minus x1 would be 0. But when I put x1 here, x1 minus x naught divided by x1 minus x naught is 1. So it's almost like L1 switches on when I put in x1, and that's what I want to ensure to do. So that way I can produce y1 as the output. You know, that's what we want to approximate f because we don't know what f actually is. And the idea is if we put in x1, we should output f of x1, which is y1. Now, the question is, so I said the Lagrange interpolating polynomial. Now, what about the secant line from last time, right? Is p of x, the one that I have here, identical to the secant line through those 2 points, which we found to be y naught plus y1 minus y naught divided by x1 minus x naught times the difference between x minus x naught. We found that using point-slope formula, and the answer is yes, they're identical. To see this, it's a little analysis trick. You add 0, but not just any 0, I'll tell you which 0, to p of x, so that you can rewrite it in a way that it looks like L of x. So I start with p of x. I'm going to need space for this. I'm just going to write what's there. In fact, I'm going to go ahead and copy paste it. There's p of x. Now, the 0 that I'm going to add to it specifically is the term x minus x naught divided by x1 minus x naught times y naught. Since I added that term, I'm going to subtract the same term away. X minus x naught divided by x1 minus x naught times y naught. So these two terms are the same thing. I've just added and subtracted them, so I've added 0. And now the rearrangement happens. I'm going to collect this term and this term and worry about this term. So you can think of, let me add a little, I'm thinking of this as like term 1, term 2, term 3, and term 4. So I'm bringing to the front terms 1 and 3, and I'm going to leave terms 2 and 4 for later. So I can get the shared denominator. I'm going to factor out a minus from that first term so that I don't pick up a minus. Let me maybe put this in a different color here. I'm going to take out a minus 1 from this term and a minus 1 from that term. And that switches their order. So I've got, on top, I've got, instead of x minus x1, I've got x1 minus x multiplied by y naught. And now, with taking out that minus, which I haven't written down, just visualizing, I'm going to have, on the denominator side, I'm going to have x1 minus x naught. Right, so just maybe a little thought bubble over here, that x1 minus x naught equals minus 1, let me make a little more space in my thought bubble, minus 1 times x naught minus x1. And I'm doing the same thing on the numerator on the top, and so the two minus 1s that you pull out actually cancel each other. I didn't need this much space, so I'm going to move this over a little. Now, the rest of term 3 is x, the numerator, x minus x naught times y naught. Very good. The reason why I did that, hopefully you can take a look, see what terms I can combine. I'll have y naught multiplied by x1, y naught multiplied by minus x. I'll have y naught multiplied by x, and y naught multiplied by minus x naught. So I have a minus xy naught and a plus xy naught. Those two terms are going to cancel. So that's what I was hoping for, something that leads to cancellation. And I still have to deal with terms 2 and 4. And so, after cancellation in that minus x plus x, that means I have left an x1 times y naught and a minus x naught times y naught. That's what's left. And I write on top x1 minus x naught multiplied by y naught divided by x1 minus x naught. Well, that was convenient. Get some cancellation going on there. I still have to deal with terms 2 and 3, so I'll go ahead and write them down. Term 2 was x minus x naught divided by x1 minus x naught multiplied by y1. In term 4 was, and there's a minus x minus x naught divided by x1 minus x naught times y naught. Now they already have a shared denominator. And here, let's see, x1 minus x naught, x1 minus x naught, I get cancellation. So I'm just going to go ahead and write a y naught plus the terms that share that denominator, x1 minus x naught. On top I've got x minus x naught multiplied by y1 coming from this. And then I've got the minus x minus x naught multiplied by y naught coming from here. Now if you take a look, x minus x naught, that's a common term. So I'm going to write this as y naught plus, I'm going to write down the y1 minus y naughts. That's this minus that divided by x1 minus x naught, because I'm factoring out the common term x minus x naught, and there you have it. If you compare L of x with P of x, they're identical. Now, a quick fact. This is going to be true no matter the size of your data set. The Lagrange interpolating polynomial between 2 points is unique. Now, as a really quick example, let's determine the Lagrange interpolating polynomial through 2 points. I'll tell you which 2 points. We'll write 2, 4. Let's say this is x naught, y naught, and 5, 1. That's x1, y1. Now I'm just going to go ahead and use my p of x setup. Remember, 3 and 4 were extra. They were the plus minus of the same term. And I'm going to go ahead and write it out. P of x is equal to x minus x1 divided by x naught minus x1 times y naught, so that when you plug in x naught you get y naught, plus x minus x naught divided by x1 minus x naught multiplied by y1. And so now I'm ready to write this down. X minus x1. x1, I can see here, is 5. X naught, I can see here, is 2. So I've got 2 minus 5 multiplied by y naught, which is 1. I'm sorry, y naught, which is 4. And x minus x naught, I can see x naught is 2, divided by x1, which is 5, minus 2, multiplied by 1. And this is the form that I prefer your answers stay in. Don't try to simplify this. And just leave it like that. Now the goal, so typically we have pretty large data sets, and we want to have a way to know information between data points. This has applications in different areas like physics and chemistry and things like that, other science areas. So the goal is, let's construct an nth degree polynomial that interpolates n plus 1 many given data points. So data is given, and it looks like ordered pairs, for example. X naught, y naught, x1, y1, all the way up to xn, yn. These are given. This is n plus the 1 because I started from 0 there. And from that given data, we want to approximate the unknown function f that generates the data. So that means f of xi are the output values yi. You might, depending on when, for example, measurements are taken that produces data, you'd want to know how you expect your phenomenon to behave in between when you weren't taking experimental data. And so that's one of the reasons why you might want to do this. And we want to do this, the approach here is by the best polynomial. For a number of reasons: the relative simplicity of the behavior of polynomials, and we're motivated and justified by the Weierstrass approximation theorem. Moreover, there's a systematic way, and I'll say systematic and relatively simple, to produce polynomials that interpolate data. I'm going to introduce higher power switch polynomials. So interpolating between two data points produced first degree switch polynomials, or intermediate polynomials. But when there's more than two data points, there's a pattern to how we produce these, and they have a couple of indices involved. So they're intermediate polynomials, so they're not quite the Lagrange interpolating polynomials, and they have a couple of indices. So something that you might want to watch a couple of times. So here's what they look like. We'll call them L like before. There's two indices involved, N and K, and I'll say real briefly that the N is the degree of the polynomial, both the L and the degree of the polynomial L, as well as the degree of the interpolating polynomial, and K is the data position that this polynomial switches on. Okay, so this is a long thing to write down, and I'm going to go ahead and write like this. It's the top, and I'm gonna write down like this. On the top, I have my x minus x naught times x minus x1, and I'm going to start listing out these monomial products until I get to almost the kth one, x minus x sub k minus 1, and I'm going to omit the kth one, x minus xk plus 1. So again, I've omitted the kth data or node. I'll introduce that terminology in a little bit. And I keep doing my product like that until I get to x minus xn. And in the denominator, I'm going to have x sub k minus x naught times x sub k minus x1. And I'm going to continue that product, xk minus xk minus 1, xk minus xk plus 1 times xk minus xn. And so what happened, since we omitted the kth data, when actually we replace x with xk, we're going to get the same numerator and denominator, and we'll get 1. But if we introduce any other data value, one of these will be 0. So it switches on only at xk and switches off for every other data. So this is happening for k going from 0 all the way to n, and with this definition, lnk of the kth data value is going to equal to 1, and lnk of any other data value is going to equal to 0 for any j that's not the same as k. If you try to define a degree 0 version of this, where there's no data and there's a degree 0 polynomial, this is identically 1. Okay, now a slight graphical, I'm going to try to draw a generic one of these polynomials. So you've got your data, x0, x1, all the way up to x sub k minus 1, xk, xk plus 1. They don't have to be evenly spaced out, but x sub n minus 1, x sub n, and let's say that this is a height of 1. Only at xk, this is actually achieving the height of 1. Everywhere else, it actually has to be 0 at these other values. And so if you start playing around with these and start trying to graph these, they'll generally take some kind of shape like this. So there's some symmetry, and because of this having to go through the data and value and have an output value of 0, the more data, the more ups and downs, that means more oscillations. That's one of the downfalls of the Lagrange interpolating polynomials. Now, a fact: for a given data set with n plus 1 data points, I'll call this x naught f of x naught, which is the same as x naught y naught, all the way up to xn f of xn, which is the same as xn yn. This is the n plus 1 many data points. There's a unique polynomial of degree n. It's actually of at most n, such that that polynomial evaluated at the node values x sub k produces the output data values f of xk. And this is what that's what we mean when we say P interpolates the data. And so just a quick little terminology: the data domain values, the xk, are also called nodes. F of xk, the output data values. And sometimes they're just called data, and the domain values are called the nodes. Okay. And that polynomial, that unique polynomial, here's the systematic way to define it, is given by P of x is equal to, and I'm going to go ahead and introduce a little subscript here for the nth degree polynomial, P of x, and I'll write by the nth degree Lagrange interpolating polynomial, it is the only one, equal to f of x naught product with L sub n0 x, the switch polynomial that turns on for the 0th node value, plus f of x1 ln1 of x. That one turns on at the x1 node value, all the way up to f of x n ln comma n of x. Now, I want to say one more thing about the associated theoretical bound, and maybe one technical thing on this next page. Note that if you only have one data point, x naught f of x naught, then your degree 0 polynomial p naught of x is identically f of x naught. You output the constant only. There's only one data value, x naught, the corresponding f of x naught, output value. You don't know the function f, so the degree 0 polynomial is a constant function. There's only one data point. That's the n plus 1 data point, and so your n is 0. The degree 0 polynomial is this constant function. Now, the associated theoretical bound, and we'll be working more with this. Let's suppose x naught, x1, all the way up to xn are n plus 1 nodes. Again, those are the domain values associated with our data. in an interval from a to b, and a theoretical function that's producing our data is n plus 1 times continuous in that interval from a to b. And that's not too unreasonable. It just says that whatever phenomenon we're looking at is relatively continuous. Then, for each x in that interval from a to b, a number called c associated to x, this is a value that's generally unknown and not the focus of this theoretical bound. The important thing is that this value exists with the following property. Okay, so we denote by p sub n of x the nth degree Lagrange interpolating polynomial. And here I'm going to write it down in the following way. P sub n of x. In the previous page, I expanded it out. Here I'm going to write it in its compact form using summation notation. The summation starts at the index k is equal to 0 and ends when I've written down k is equal to n. And I've got f of x k multiplied by L sub n k of x. So the independent variable x is here in the switch polynomials, where f of xk are the generated output data for k's going from 0 all the way to n. And with the switch polynomials, and I'm going to write these in there also using a compact notation. ln k of x we know is this long product, so I'm going to use product notation using a capital pi. This product is happening over the indices j is equal to 0 to n, but omitting when j is equal to k. And what we're going to take the product of are these monomials x minus xj divided by the constant values xk minus xj. And this is working for n bigger than 0. Really quickly, I'm going to copy paste that ln k so you could see that this is the same thing. You can see here when you start your counter j is equal to 0, you put 0 here, right? There it is. You put 0 there, and that one is your j is equal to 0. You increase your counter to 1, and there it is. The k always stays down here. Okay, and this is that giant product. And these switch polynomials have the property ln k at a node, let's say xi. Two things can happen. You get 1 if the entry xi is the kth entry, and 0 if I is any other node value, not the kth entry. So this is happening for the node input values. You have n plus 1 many entries. And so here's the theoretical bound. With all of that in place, right, you have the Lagrange interpolating polynomial made with those switch polynomials defined this way. Then that function that you are in the search of approximating is precisely the Lagrange interpolating the Lagrange interpolating polynomial plus an error term, the part that you remove from your approximation when using Pn of x to approximate f of x. And it is the n plus first derivative of f evaluated at that theoretical value that you won't be able to determine, divided by n plus 1 factorial multiplied by a polynomial x minus x naught multiplied by x minus x1 all the way up to x minus xn. This is a product. So what this means is if you're using Pn of x to approximate f of x, you can always determine the absolute value. You can always determine the absolute error by estimating a bound on this error term. So, for that reason, this term is either called an error term or Lagrange remainder term. Now, in our next class period, we're going to have an activity that I'll post on Canvas now. It does need some careful reading, so please take close attention and notes and come ready for a fairly intense activity at our next class time. See you soon.